Hello, my name is Juan Reyes. I am a civil engineering student at the University of Texas at Tyler, and today I will be presenting my final research presentation for the course Geology 3314, Oceanography and Meteorology, taught by Dr. Teresa Kennedy. And my research topic of choice was engineering resilience, designing coastal infrastructures to withstand extreme weather. So without further ado, let's get started. So I want to start off with the question, why is it important to build durable infrastructure? And well, the answer might be obvious to most of you. Why would someone invest thousands of dollars or even millions in building something, in building a structure, a facility, or infrastructure if they are prone to collapse and may collapse within a short time frame? So, for sake of both safety and economics, you want to build your buildings to last. I want to draw your attention to a common saying in Christian circles, to build one's house upon the rock, meaning to build one's life upon moral principles. But this also has a literal application as well, as we must diligently design and build our homes, infrastructures, and essential facilities to withstand the inevitable trials to come, particularly in terms of extreme weather events like hurricanes, tornadoes, and earthquakes. And as engineers, the safety and well-being of the public rests on our shoulders. And although we engineers are not data or climate scientists, but we do make use of oceanographic data to account for the threats posed to the structure, so as to diligently and make an efficient design. So what will you learn throughout this presentation? You will learn how engineers use oceanographic concepts and oceanographic data to assess the wind, rain, flood, and possibly even seismic loads to be exerted on the structure in order to accurately model it as best we can. And you also learn how we take uncertainties into account. So obviously, it is not possible to uh, simulate a tsunami or an earthquake or wind loads to 100% precision or accuracy. So there is always uncertainties, and we do take certain steps in due diligence to account for these uncertainties. And you will learn a bit of that throughout this presentation. So essentially, engineers design buildings, infrastructure, and other facilities following design and building codes, which are essentially standards set out by governing institutions, which dictate the designs of structures. And these codes take into account the various threats posed to the structure, the various loads, the trials and tribulations that are to be exerted on it. And the codes take these things into account, and they also provide us with provisions and contingencies to use in those structures. So, to provide a bit of a history on design codes, in North America and particularly New England, they saw their first implementation of regulatory building codes as far back as 1625, as long before we declared independence, and this was mostly related to fire and egress concerns. So as I mentioned before, the purpose of building codes is to provide valuable standards and codes to follow for the efficient designs of buildings and infrastructure. And our goal as engineers is to design not only a safe structure, but also an efficient one. So while we don't want to under design a structure so as to make it unstable, prone to collapsing, but at the same time, we don't want to over design it to make it so exceedingly strong and use an exceeding amount of material so as to make our the construction project prohibitive. So we always, as engineers, we always try to look for the most efficient solution, but that solution has to be safe and viable as well. And some key terms that go with the design of structures are obviously loads. Loads are essentially forces exerted on an object. Force equilibrium is established by Newton's second law. So essentially, uh, a if an object acts on a force, it will accelerate, right? In order for an object to stay at rest, a counteracting force must cancel that force out. This is force equilibrium. Strength is essentially the load bearing capacity of a structural element, and serviceability primarily deals with deflection, with occupant comforts. So a building might be relatively strong, but it might be also extremely ductile and prone to deflections, even though it doesn't collapse. We don't want that either, so we take both strength and serviceability accounts in our designs. So to essentially set the tone of this entire presentation, engineers, we work with a lot of code books, but the most common ones that we use are these two: the American Society of Civil Engineers, minimum design notes and associated criteria for buildings and other structures, as well as the International Building Code. These codes are updated on a regular basis. The International Building Code, also known as the IBC, is updated every 3 years, in fact, and the American Society of Civil Engineers, this particular provision, which is also known as ACE 722. It is updated every 5 to 7 years, just to account for new new research data. So the American Society of Civil Engineers, this particular codebook provides us with the loads, with the minimum loads to be exerted on a structure based on the geometry of the structure based on its location. Wind loads vary by location, by geographic location as well. And the International Building Code deals with architectural provisions or contingencies to ensure our structure stays resilient in the case of flooding, earthquakes, or other stuff. So these are two of the most representative provisions from the International Building Code that I want to draw your attention to. So the first one of which is Section 1604.5. The section is talking about risk categories, and it is precisely the section referred to in this image. So the International Building Code assigns risk categories to buildings depending on the threat that they pose to human life. It goes, they range from risk category 1, which for structures that pose a low threat to human life in the case of collapse or failure. So examples of these types of buildings would be minor storage facilities or agricultural facilities like barns. If they were to collapse, there would be economic losses, but there will be minimum threat of life. And the other end of the spectrum is risk category 4, which are what are called essential facilities. If these facilities collapse or fail, then it will pose a viable threat to human life and also to the function of society. Examples of these types of buildings include hospitals or radio broadcasting stations. So, God forbid that a hospital housing many people in the ICU were to suddenly collapse, killing all those occupants, including all those patients inside. So we base our designs, the level of strictness of our designs depends on the risk category, and this is essentially what it's about. Another one that I want to draw your attention to is Appendix G, and this talks about flood-resistant construction. So for example, this provision requires that the lowest opening or floor of a building be located above the flood elevation line, so as to try to minimize the risk of flood water sneaking into your home in the case of a major flood. So some of the representative provisions of the ACE include section 26.5.1, which talks about basic wind speeds. What a basic wind speed it is essentially the maximum 3-second gust wind speed that is expected in the region where the site is being built. So as I mentioned before, wind speeds and wind loads vary by region. And based on your geographic location of the building site and the risk category assigned to the structure, engineers will have to account for a maximum 3-second wind speed to use either as their design loads. So, for example, if you look closely at the Houston area, I know it's small to see, but if you squint your eye, you can see that The basic wind speed here is 130 miles an hour, and obviously this wind doesn't blow all the time. There's a maximum wind speed that occurs over the span of 3 seconds, and this represents the worst case scenario. So that's where we're going to design for worst case expected scenario. The AAC also has provisions on rain loads on roofs, hydrostatic flood loads for dams, for instance, and essentially this is where this is the provision. This is the code book where we get our loads from to simulate our structure. So um, I can't close this presentation without talking about the importance of satellite missions. Satellites provide us with updated knowledge on the nature and dynamics of storm events. And two of the most recognizable missions include GeoSats, which launched in 1985 and ended in 1990. And these satellites provided us with the first detailed global measurements of ocean topography and variations in the seafloor. And you may be wondering why the shape of the ocean floor is relevant in the design of infrastructure and buildings. But surprisingly, the nature of the ocean floor can have a direct impact. It can either mitigate or it can either magnify the effects of tidal waves and tsunamis. And it is also directly intertwined with plate tectonics, which is essentially is at the core of seismic loads and seismic design. Another important satellite mission is Jason 3, which is an ongoing mission launched back in 2006. This satellite measures sea surface heights, wave heights, and ocean currents. It helps us better understand the dynamics of storm formation, as well as the magnitude and the intensity of waves. As I mentioned, the code books get updated regularly, every 3 to 7 years, and they are updated based on updated the latest data provided by these satellite missions. So that will be their satellite missions' direct contribution to resilient structural design. And as I mentioned previously, engineers don't directly work with satellite missions. We don't directly we don't directly interpret oceanographic data. Rather, experts crunch this data and they put it together in these code books, and we reference the code books in our design. But these code books wouldn't be possible without without the extensive work of weather scientists. So to give an example, ACE 722 draws its data from NOAA, and NOAA in turn uh, gets provided with data from many of these satellite missions, particularly Jason 3. And I want to conclude, I want to set a tone for collaboration between scientists and engineers. So, although these are two different professions, hopefully in this presentation you learn how engineers use oceanographic concepts and oceanographic data. Maybe not in a direct way, but in an indirect way in their designs. So as you can see in this Venn diagram, scientists are investigators. They are observers. They develop or they discover rather scientific principles. They establish um, what we believe as science, and engineers then use this data they to the benefit of society. So you can say that engineers build upon the work of scientists in order to design resilient structures themselves. So hopefully this concludes my presentation. Hopefully you all have learned something to learn the basics of an engineer's approach to designing a building and to account for the possibility of extreme weather events. I particularly gave the example of wind and flood loads, and hopefully you could also see the um, the level of collaboration really between these two disciplines, scientists and engineers, particularly civil engineers or structural engineers to design your infrastructure and facilities. But I can't emphasize enough that their work wouldn't be possible without the extensive work of scientists, engineers, and all the extensive research that they do. And that's it. Thank you.